Now we will discuss about the chapter real numbers. Already you know the different types of numbers, the number system, the natural numbers. There are other type of numbers already you know, that is whole numbers as integers, then fraction, then rational numbers, irrational numbers, decimal numbers. Like that, so many numbers already you know. Okay, now we discuss about the real numbers, means what numbers you know already, that all numbers are together known as real numbers. Okay, then this is natural number. N is actually 1, 2, 3, etc. like this. This is known as natural numbers, otherwise counting numbers. Then this is whole numbers. Natural numbers all there including 0. That is 0, 1, 2, 3 like that. This is whole numbers. Then integers. Integers means 0 is already there. Then positive numbers 1, 2, 3 like this. And this side also negative 1, negative 2, negative 3 like that. That is known as integers. Okay. Then fraction, you know, that is normally P by Q form, where P and Q are natural numbers. Suppose fraction. Fraction, P by Q form. P, comma Q are natural numbers. P and Q are natural numbers. Suppose example 1 by 2. 1 is the natural number, 2 is another natural number. 3 by 7. 3 is a natural number, 7 is also a natural number. 8 by 5. 8 is a natural number, 5 is another natural number. Like that, this type of, so many examples we need to write. Okay, anyway, both the numerator and denominator we need natural numbers, that is known as fraction. Next we can discuss rational numbers. Rational numbers. Okay, the rational number is also P by Q form. Same numerator and denominator we need. P and Q are, and here P and Q are natural numbers, here P and Q are integers. P and Q are integers, that is the difference between fraction and rational numbers. Okay, P and Q are integers, and one more condition is there, Q not equal to 0, because integers including 0. The division by 0 is not defined now, therefore denominator is not equal to 0. For example, 2 by 3, 2 is an integer, 3 is also another integer. Minus 5 by 7, minus 5 is an integer, 7 is also an integer. 3 by minus 8, 3 is an integer, minus 8 is an integer, for this is considered as okay. Then 0 by 7, 0 is an integer, 7 is also an integer. Okay, but 2 by 0, here denominator is 0, that is not possible. Okay, integers consider like that. Okay, then now we discuss about irrational numbers. Irrational numbers. Okay, irrational numbers means like this: root 2, root 3. Root 4 already you know that is equal to 2, therefore that's no need to consider. For root 5, like that numbers, that is considered as irrational numbers. Now we discuss how many types of numbers: natural numbers, whole numbers, integers, fraction, rational numbers, irrational numbers, and so many remaining the decimal numbers like that. Anyway, this all known as, together known as real numbers. This all together known as real numbers. That is we discuss here, real numbers. Okay. Now we discuss Euclid's division lemma. Okay, Euclid is the great mathematician, that Euclid's division lemma we can discuss now. And the statement is like this: given positive integers a and b, when we consider two positive integers a and b, there exist unique integers q and r. Q and r are normally quotient and remainder like that. Q and r satisfying this condition: a equal to bq plus r. Here a and b are two integers. Okay, then a can be expressed bq plus r. The one more condition is there, the remainder always less than b. 0 less than or equal to r, the remainder less than b. We need to satisfy that condition. Okay, you can give an example like this. Suppose when we are dividing 23 dividing by 4. Suppose when we are dividing 23 dividing by 4, normally we got like this 5 into 4 20, remainder 3. That can be expressed like this, 23 equal to 4 into 5 plus 3. This is in the form of like this, that is, and this is considered as a equal to, this is b into quotient is like that 5 plus remainder is, this is q and this is remainder r in this form. Any number, when we consider dividing by any number, we can always express like this, 23 equal to 4 into 5 plus 3, here a equal to b into q plus r. This is known as Euclid's division lemma. Okay. Now we discuss Euclid's division algorithm. And normally you know that is algorithm is a step-by-step process. Algorithm is mainly used for, okay, this here Euclid's division algorithm is used for finding HCF of given two numbers. Okay. Euclid's division algorithm. It is used for finding HCF of two numbers. Okay. Suppose finds HCF of 20 and 6. Let's take and explain this question. Okay, 20 and 6. You know that form is like this, a equal to bq plus r. Here two numbers are 20 and 6. We can consider which one is greater. Already you know which one, when we comparing this 20 and 6, which one is the greater? Yes, 20 is the greater. Therefore, that number we can take as a. So here we can take as a as 20, b as 6. The normal division, this 20 can be expressed like this, 20 equal to 6 into 3 plus 2. When we are dividing 20 by 6, the quotient is 3 and remainder is 2. The division already you know. Okay. After that, we can consider next step, this is a and this one is b. Therefore, 6 can be expressed. 6 equal to 2 into 3 plus, what's the remainder? Remainder becomes 0. When you got the remainder as 0, you can stop there. In that time, which term is here, and this is considered as, this here also, considered as HCF of these two numbers. Therefore, here we can write like this, HCF of 6 and 20 equal to 2. The larger number we can take as 20 and a smaller number we can take as b, a and b, and that can be expressed like this. Here only two steps, sometimes we need so many steps for when you get up to 0. Okay, when you get 0, in that time which number is here or here? Both are same. Okay, that is considered as HCF of that two numbers. Clear? Okay, and one more question I can give you. HCF of 135 and 225. Here again two numbers. One we need to find out HCF of 135 and 225. Here you know which one is the greater one? 225, that everyone know. Okay, then a equal to 225 and b equal to 135. Again we can find out, can be expressed that form, a equal to bq plus r. After division we need to find out for 225 equal to, so we can divide like this, 225 dividing by 135, that is 1 into 135, 135, 0, that is 90. Then 225 can be rewritten like this, 135 into 1 plus 90. Now this is in the form of like that, a equal to bq plus r. Then next we can start like this 135. 135, this is A and this becomes B. That is 90 into 1 plus 45. 90 into 1, 90 plus 45 is actually same. We can divide and find out that. Okay. Now 90 equal to 45 into 2 plus 0. Now we got the remainder as 0. In that time, which number is here or here? That is 45. Therefore, when we get the remainder 0, this number we can consider as. Therefore, answer is HCF of that two numbers 135 and 225 is answer 45. Like that, we can find out HCF of two numbers by using Euclid's division algorithm. Okay. The next question is like this. Use Euclid's division lemma, the same lemma we can use here also, to show that the square of any positive integers, the square of any positive integers is either of the form 3m or 3m plus 1. We can find out the square of a number can only in these two forms, 3m or 3m plus 1. Okay. Same model we can take A equal to, the normal form is like this, A equal to BQ plus R. Here with the 3m is there, therefore B we can take as 3. 3m plus 1, B equal to 3. Therefore it can becomes, remainder becomes 0, 1, 2 only, less than 3. Okay. Now we can start like this, A equal to BQ plus R. That form we can express first. First we can take R equal to 0. R equal to 0 and this becomes A equal to 3Q plus 0. That is A equal to 3Q. Here we need square of, therefore we need to square of that. That is A square equal to, A square is equal to 3Q square. That is 3Q square becomes 9Q square. 9Q square can be written 3 into 3Q square because 3 into 3 is 9. This bracket is simply considered as m, therefore it can be expressed as 3m. Clear? This I can explain again. Suppose first we take R equal to 0, then A becomes 3Q. Now we can take A square because we need the square of. So A square is equal to 3Q whole square, that is 9Q square. 9 can be taken 3 into 3Q square. This 3Q square just taken as m, the new variable, therefore 3m. First one, okay. Now we can take R equal to 1. R equal to 1 means A equal to 3Q plus 1. That's what we need. A equal to 3Q plus 1. We need again square of. We can take square. A square is equal to 3Q plus 1 whole square. A square is equal to 3Q plus 1 whole square. This is A plus B whole square form. A plus B whole square already you know. This A square plus 2AB plus B square. Okay, that we can use here. A square plus 2AB 2 into 3Q into 1 plus B square. That is 3Q whole square becomes 9Q square plus 2 into 3Q becomes 6Q plus 1. That's again from these two terms we can take 3 outside, that is 3 into remaining here 3Q square plus 2Q. From these two terms only we can take 3 outside plus 1. That's again in the form, this is considered as m. Therefore it becomes 3m plus 1. This is another form, 3m plus 1. Square of second number, when we take R equal to 1, we got like this in the form of 3m plus 1. Now one more is remaining there, that is R equal to 2. R equal to 2. R equal to 2 means it becomes A equal to 3Q plus 2. Because R becomes 2 means this becomes like this, A equal to 3Q plus 2. We need to find out the square of. We can take again square. A square equal to 3Q plus 2 whole square. That's again A plus B whole square form. A square plus 2AB, 2 into 3Q into 2, 2AB plus B square. That is, this can be expressed A plus B whole square form like this. Now, this becomes 9Q square plus 2 into 3, 6 into 2, 12q plus 4. Okay. Now, we can take like this 9q square plus 12q plus this 4 can be expressed 3 plus 1. This 4 can be rewritten like this 3 plus 1, that already know. From these 3 terms, we can take 3 outsides, 3 into 3q square plus 4q plus 1, close the brackets. From these 3 terms, we can take 3 outsides. 3 into 3, 9, 3 into 4, 12, 3 into 1 like this, plus 1 is remaining there. Again, we can take this as m, it also can be expressed 3m plus 1. This bracket we can consider simply as another variable m, therefore it becomes 3 into m plus 1. Therefore, the square of this when a equal to bq plus r, it can be expressed 3q like this. The square always we got 3m here, 3m plus 1 here, and here also we got 3m plus 1. It can be expressed one of the form 3m or 3m plus 1. Okay, clear.